This is part 2 of my periodic table of elements video series, and the next subject I'd like to talk about is ionization energy. And the definition of ionization energy is the energy required, excuse my shorthand here, to remove one electron from the outermost state. So while you soak this definition in, I'll explain really in simple terms what that means. So let us take, for example, the element lithium. Lithium has a configuration of 2,1, and it's going to want to lose that one electron so it becomes stable in the configuration of neon. So therefore, the energy required to remove that one electron from lithium is pretty low in comparison to the other elements. When you take the element neon, which has a configuration of 2,8, and if I said neon before for lithium, excuse me, I meant helium, and actually neon has 8 more electrons since it's in the same period. Neon has a configuration of 2,8. It's also a noble gas. So if you know noble gases are stable, will also understand this concept pretty easily, because it's not going to want to lose that one electron. So you're going to need to put in a lot of energy to remove that one electron. So the trend here is a little more complex than before, but generally as you move from right to left this time, your ionization energy is going to go down. And so the closer it is towards being less filled, the more likely that the ionization energy will be lower, and it's going to be easier to remove that one electron. Next, I'd like to talk about ionization energy. Ionic radius. And ionic radius is similar to atomic radius. The only difference is that you're now dealing with an ion versus an atom. So let us take our example of fluorine. And as an atom, fluorine has a configuration of 2,7, while an ion, fluoride, it's going to have a configuration of 2,8. And so the difference here is only the amount of electrons. It has the same amount of protons. It's still fluorine. If it has different number of protons, then it's not the same element. So they're going to trick you with that, try to trick you on the regions. Don't fall for that. The only difference is that there are more electrons in fluoride over fluorine. And if I graphically depict the orbitals here, really crudely, you have the first orbital. Actually, let's make that the nucleus. The first orbital and the second orbital, because there are only 2 orbitals in fluorine. You're going to have 7 on the outside here and 8 over here. And so there are more electrons located, 1, 2, 3, 4, located in fluoride. And so if you try to understand this logically, there are more electrons crowding around in the same orbital. And electrons, as you know, are negative. They don't want to attract. They're not attracting each other. They want to repel each other. So therefore, they're going to want to move farther apart. And we can conclude that in a fluoride ion has a greater ionic radius, or greater ionic radius than the atomic radius of fluorine, because here there are only 7 electrons, and they're not going to repel each other as much. These ones are going to try to spread out more, so they're going to increase that radius further. That's the difference between ionic radius and atomic radius. Really simple if you understand that in an ion, you have, depending on if it's a positive or negative charge, if it has a negative charge, it means that it gained that extra electron. It's going to those electrons are going to want to repel each other. The same thing goes if it's in the opposite direction. Fluorine can't be a +1, but if we take an element with a positive charge, then it's going to be the opposite case, because now it lost those electrons, and those electrons are going to repel each other less. So, in essence, it's the opposite case of a negatively charged element.